start recording. So you can refer back to this later. So right now, let's. I'm going to share my screen, and we can kind of go on like a tour of our websites. There's this unfortunate thing about Zoom, which is it puts its controls right over the tabs on your browser. But I want to talk about first of all CoCalc. So this is you should have gotten an email invitation to this site. You might not have, because usually the thing that happens to make this all go wrong is that Harold, I don't remember calling Harold's name, but you can see Harold has a Kingsborough email address, and often when people have these old email addresses, they don't check them, and so they never get the invites and stuff like that. So please try to get set up here as soon as you can. We're going to be using this site a lot. Harold obviously did get the email because he now has a members only account. So this is, we're going to be doing a lot of stuff on the command line. And so this site is basically your own Linux virtual machine with a web-based interface. It has a lot of stuff for handouts, like you already have a handout here, which are the slides that we're going to go over today in a couple minutes. So like, Eric, if he has an account here, can go and look at the slides that I'm going to start presenting in a minute, which are in the notebooks folder under lecture 1. So I'm also going to use this website for collecting your work. So for example, when I issue you a homework, there's nothing in here right now, but I might create something like homework 1, and then I'll put some stuff in here, like the instructions. And so you can read the instructions, and then on your virtual machine, you can create the files that are the answer. Most of the time, it'll be some kind of C++ program. And then when it's time to hand in the assignment, I will just push a button, and and your solution will be copied onto my virtual machine. And I find that it works really well. Another good thing about this is that it makes it really easy for us to code collaboratively. So you can see that there's a chat tab over here, and I can go to your virtual project, and we can look at documents and edit them at the same time while we talk. If you want to text me, so if you start typing here, like asking me a question, this little bell will ring, and I'll get a notification that somebody wants to talk to me about a project. But if you say @Hunter Johnson here, if you @ me out, then I will additionally get an email. And so I'll be more aware of what the issue is. So I find that this works well for writing code during office hours. We can actually look at the same screen and edit the same stuff, and it just makes everything much simpler. And it's good for people that are Windows users that don't have to go through the hassle of setting up some kind of Linux system so they can do the assignments. The downside is that it does cost a little bit of money. It costs $14 for the whole semester. So I hope that's okay. I try to make my classes cheap. You only have to, the textbook, you can buy the textbook. It's not expensive. The last time I checked, it's like $40 or something to buy. Also, you don't exactly have to be a super hacker to find the PDF. Not that I'm encouraging anybody to do that, but I will say that my own copy of the textbook is locked up in my office at John Jay, where I haven't been for a while. So I have set these somewhere here. I set, sorry, it's here. So under configuration, somebody want to say something? So I set it up so that you have to pay. I forget exactly what you have to pay by September 4th. Somebody is unmuted, which is okay if you have something to say, but if you don't have anything to say, it's making some kind of scratchy background noise. Okay. So hopefully that's not an issue, and we'll start using that immediately today. Another thing I wanted to show off was Piazza, which I like to use for communication. So I haven't looked recently to see how many people have signed up for this yet. But everybody's gotten an invitation, and it looks like most people have registered here. So I'm going to look at the participants list and see if I can find the person whose microphone is on. Tosin, that seems to be you. Do you have something to say? Okay, I'm gonna mute that. And okay, so the good thing about Piazza is that you can answer each other's questions. I can post stuff here, and you know, we could do the same thing on Blackboard, but with Blackboard, it takes so long to log in. You have to log into CUNY first, and then go to Blackboard, and then find your class, and then go to the discussion board. But if you just type Piazza, you come right here, which is the screen that we want to use 99.9% of the time. And you should have some introductory notes helping you get used to the stuff here, and I'll be posting things there as well once I'm confident everybody is on there. And there's only one more thing that I wanted to talk about, which is web work. So for the first time ever, I'm going to try to use online homework questions with the cryptography class. Oops, I don't want to log in as Matt Luba. We're working on the site together. So you can, everybody has an account here already presented the material. But we're going to be using this for some of the book homeworks. To be honest with you, you wouldn't believe the amount of effort that goes into creating one of these questions. Like some of these questions have taken me like multiple days just to create. So I'm not confident that I'll be able to keep up with the class as we go along. So I've got a couple in the bank here, chapter 1 and chapter 2. The syllabus says that we're going to do chapter 3 problems from the book, but Matt Luba has graciously written those, and I just need to put them in. So I believe we're also going to do chapter 3 questions on here. And then later in the semester, when we come back to public key cryptography is very mathematical, so it will work well with this site. And we'll come back and we'll start using this again for answering homework questions. By the way, so if you've been over the syllabus, you already know like the what you have to do. So you have book problems, and I'm calling the web work questions book problems also. So you have some kind of like homework just from the textbook. And we also have some programming projects. So this class, I'm sad to say, is just kind of strictly harder than Matt Luba's class. I don't know if you can trade off with somebody who's there, because we're going to do 6 practical, maybe we'll shoot for 6 practical cryptographic activities here using real code and stuff like that. And then additionally, we have a take-home midterm and a take-home final, and then these homework problems. And you can look at the syllabus to see what the grade breakdown is between all of those. Let me see if I think I have the syllabus already open here. So let's see if we can find the part of the syllabus that talks about how your grade is determined. So the projects are 35% of the course, the midterm is 20%, the homework is 25%, and the final exam is 20%. So that's how your grade is determined. I think you get to drop something. You get to drop like the lowest project right here. Your lowest project score will be dropped. Okay, so that is sort of the administrative stuff. And I think there's no reason that we can't start talking about actual cryptography here. If I can find my way back to where I was. Okay. So before we start talking about actual class material, anybody have any questions?
Sorry, about Kirkhof. I haven't registered for it yet. But did you say that we were going to have to pay for the members only?
Yeah, it's $14, and it really makes it work much better.
All right, no worries. I just wanted to make sure that we had to go through with that.
Okay, cool. Thank you. It might be the only $14 you pay for the course if the textbook has to fall off it happens to fall off a truck in your neighborhood.
All right.
Okay. So if you are on CoCalc already, then you should be able to go to Cryptography Fall 2020, and under Notebooks, Lecture 1, there's some slides here. This is an IPython notebook, and I'm going to be presenting the slideshow here from a local copy, but you can follow along there if you want to. Okay, and you don't have to know crypto for the course, obviously, but cryptography works really well with Python because you have these notebook things for one thing, and then the libraries work really nicely. Also, Python you can use arbitrarily big numbers, but in C and C++, you know, you have like 8 bytes to work with, which is not big enough to do cryptography. Okay, so the lecture today is on classical cryptography. So this is cryptography that is up to World War II, and in some ways cryptography that was used during World War II. It is kind of amazing how bad cryptography was. I guess maybe they didn't have computers, so you know the ability to crack these codes wasn't also as powerful. But basically, all the crypto up to World War I, we're going to learn how to break in the next 45 minutes. Most of it was based on the idea of just substituting letters in messages. There's famous examples of substitution ciphers. We're going to talk about Caesar's cipher, which was used by the Roman general Caesar. There was a famous political plot involving the successors of Henry VIII. Like there was Mary, Queen of Scots or something, and some people wanted Mary, Queen of Scots to be queen. Some other people wanted Queen Elizabeth to be queen. And there was this secret plot in which they were using a substitution cipher to communicate, which was promptly cracked even back then, and everybody was executed. Okay, so I don't want to make too big a deal out of this library that I'm using. I'm using a library called SymPy to do this basic cryptography. You don't have to learn how to do that. It's just a convenient way for me to present things. All right, so just some terminology. The information that you want to encrypt is called the plaintext. And you know, you have modern cryptography works with computer files, not with written English. But with these, you know, toy examples that we're going through today, we're mostly going to be encrypting written English. So here's some written English. Often you want to get rid of all the spaces and punctuation and convert to uppercase. So that's what this little function does. So our plaintext will look like that. When they actually use this kind of cryptography, like back in World War II, often they would break it up into groups of 5 just to make it a little bit more readable. But essentially it was just like this. Okay. So what you're going to encrypt is the plaintext and the resulting cipher is the ciphertext. So the way you get from the plaintext to the ciphertext is through the encryption algorithm. Our booklet uses a lowercase e for the encryption algorithm, so I'm going to use that too, even though it's a little weird. All right, and there's also some secret piece of information called the key. So we're talking about maybe text documents and things, but in a digital world, everything is a number. You know, all information can be represented as some file on your computer. File on your computer is basically a number. So you can think of these things as functions that have basically numbers as their domains and their ranges. We think of a key as being a number. Usually you say that a key is a certain number of bits long, like you might have heard of 128-bit cryptography. That means the maximum length of the key is 128 bits. Other kinds of cryptography, though, we're going to talk about some exotic situations also. So the set of all possible keys is called the key space. The message space is the set of all possible messages, which just think of them as numbers. And the ciphertext space is the set of all possible ciphertexts. So you can also think of those as numbers. So we'll never actually write down the message space or the ciphertext space. All these spaces are too big to actually write down, but we can still use them in our notation to sort of present things in a nice way. So here's the basic setup. You take a message and a key and produce a ciphertext. So E is the encryption algorithm, M is the space of all messages, K is the space of all keys, C is the space of all ciphertexts. So in case you've never seen this notation with this big cross before, this is the Cartesian product. So it just means all pairs. So the first thing in the pair comes from the message, and the second thing in the pair comes from the key space. So this just means all pairs of keys and messages. And our book always uses X to denote plaintext and Y to denote ciphertext. So I'll try to do that too. Sometimes you use this notation. So here's the encryption function with a subscript K. And that means we're going to be encrypting and the key is already fixed. So then that is just a function from the messages to the ciphertext. Okay, so just looking at this function, this has to be a little bit of a special kind of function because you don't want to just destroy information. You want to encrypt it and then later decrypt it. So that means that the encryption function has to be invertible. So you have to be able to go backwards as well as forwards. So the inverse, I should have put a little subscript K here too. The decryption function is just the inverse of the encryption function. It goes from the ciphertext back to the message space. So if you take the decryption of the encryption, you should get the original plaintext back for any plaintext, right? So that's not surprising. And how does encryption actually work? Well, there are tons and tons of encryption algorithms. So we can look at our first example here. This is called the Caesar cipher, which was supposedly used by Julius Caesar. You can read about it if you follow this link here. This is an example of something called a shift cipher for reasons that we'll say in a minute. So let's just look at the output here. So the plaintext is, this is the plaintext, and the ciphertext is blah, 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 and the decrypt is, this is the plaintext. We're going to kind of go over that in slow motion now and explain what just happened. So this is an example of a shift cipher. So the way all these old classical crypto things work is you identify each Roman letter with a number. So there are 26 Roman letters. So you get numbers in the range from 0 to 25. And what the Caesar cipher does is it just shifts everything forward by 3. So if you look at now the index of A is not 1 anymore, it's 3, and the reason they call it a shift cipher is this kind of happens circularly. So it's like everything in the right hand side here gets moved up by 3 ticks. So now A is 3, B is 4, C is 5, D is 6, etc. And down on the bottom here, Z has become 2, Y has become 1, and X has become 0. So this is using modular arithmetic. Everybody had to take 204, so hopefully you're kind of familiar with modular arithmetic. We're going to be using it for everything. It's almost true that every cipher uses modular arithmetic in some way. I think actually it's literally true. Every cipher uses modular arithmetic in some way. So the index is going to the index plus 3 mod 26. That means the remainder when you divide by 26, right? So if you add 3 to 25, then you get 28. But the remainder when you divide 28 by 26 is 2. So that means Z is 2. Okay. So now we get a correspondence. So this is the actual substitution that gets applied. So all of these ciphers that we're going to be talking about are substitution ciphers. So what happens is every time you see an A, you substitute D, which is the 3rd letter. Every time you see a B, you substitute E, which is the 4th letter, and so on all the way down. So all the X's get turned into A's, etc. So now you can see the result. So here's an actual piece of plain text. So if you look down the column here that says this is the plain text, and T gets circularly pushed forward 22 spaces and becomes a W. H gets circularly pushed forward 10 spaces and becomes a K. So if you saw this ciphertext, it does look like nonsense. You know, you can't read this message at a glance. So to do the decryption, you need to circularly rotate things the other way by 3 ticks. So you can think of it as sort of, you know, spinning the wheel down by 3. But because it's a circle, you know, spinning one way by 3 is the same as spinning 23 in the other direction. It's kind of hard to visualize, but if you can imagine like a combination lock, like a combination lock on a locker, every left-hand turn is equivalent to some right-hand turn, right? If you go left and you could have done the same thing by going right a certain amount. So this is just saying that going left by -3 is the same thing as going right by 23. So usually we try to work with numbers that are always between 0 and the modulus in this case being 26. So we kind of prefer 23 here. You can see that Python considers this to be true, that -3 mod 26 is the same thing as 23 mod 26. By the way, notice I used congruence sign here instead of an equal sign. Hopefully you saw that notation in 204. I don't know if you did or not. Anybody see that or not see it? I'm going to explain it here, but did you see it in 204?
Yeah.
Okay, great. So what this symbol means, we say A is congruent to B mod n, means that A and B have the same remainder when you divide by n. So if you divide -3 by 26, what would you do? Like 26 goes into -3 -1 times evenly, and then the remainder is positive 23. That's kind of hard. The negative number is a little bit strange. So in cryptography, everything is an integer. We really don't do anything with floating point numbers. So A, B, and N are all integers. You've hopefully seen this symbol Z before. In math, we use Z to represent the integers. It's because a German mathematician started this tradition, and in German, the integers are number, I think, is Zahlen. Another way to understand this congruence relationship is that that if you take the difference of these two, if you do A minus B, it doesn't matter if you do B minus A or A minus B, but if you do A minus B, then that difference is divisible by n. That's another way to understand modular congruence here. So if you look at -3 and 23, if you take the difference of -3 and 23, you get -26, which is divisible by 26. If you do it the other way, you get 26, which is divisible by 26. So these two numbers are congruent because their difference is divisible by the modulus. So here's a picture of this happening. I keep saying circular shift and things like that. Everything that happens in the modular world, you can think of it as happening on a sort of a big circle. So you know, the number line is an infinite line that goes on infinitely in both directions. But when we mod out, that's the ends sort of get tied together, and you get kind of a finite circular object where you can go forwards and backwards. Okay, so here we actually do the decryption. Here's the decryption part. So you initially have some letter. This part might seem strange to you. What OR does is it gets the ASCII code for a letter. And maybe we should just take a quick digression over here and look at ASCII. So you can type this into any terminal. You can also just Google man ASCII and this same table will come up. Personally, I look at it all the time. But you've probably seen that so here are the things that we're going to be most interested in this class. It's just the Roman letters. So in ASCII code, an A is represented by 65 in decimal, In hex, that's 41. And so the capital Roman letters go from 65 down to 65 plus 26, which is 90. Okay. And if you look at a document that actually is made up of text, and then you look at the binary for that document, look down here at the bottom of the screen. Maybe I'll clear and then do that again. So here, what you'll see is if the binary of this document is just the ASCII encoding of each letter. So this is hex 54 is the same thing as T. Hex 48 is the same thing as H, and so on and so on and so on. Okay, so let's come back to this presentation. So what the ORD does is it takes a letter, which is one of these. I know this is in Python, but you have to do the analogous thing in C when you code this up. So that's why I'm spending a long time on it. So if I do ORD letter, and let's say letter happens to be T here, then T will get converted into its ASCII numeric equivalent. And we can look back and see what that actually is. No, let me just show you here. So what is ORD? ORD T happens to be 84 in decimal. So if you take away, now 84 is not a number between 0 and 26, right? But it is if you take away 65. So when you take away 65, then you get 19. And that works well because back here when we originally set up our correspondence here, T is the 19th letter of the alphabet when you start the indexing at 0, so you want to think of T as 19 for the purposes of this cipher. Okay, so here you do the Caesar encoding, and this K is the reverse. So you take the transformation that you did, you send it forward 23 more times. So by this time, the original encoding is spun around a full 26 times. It's spun around the loop entirely once. And so what happens is it decrypts the ciphertext. So here you've got the plain text, the ciphertext, and then the decryption. So I hope that's clear. Maybe you've heard of like encoder rings. So this is the Caesar cipher is basically an encoder ring cipher where the inner circle is ticked over by 3. You know, that shows you a correspondence between the letters, and so you decrypt the message that's on your Ovaltine box and mail it off and get a prize. So here's the mathematical description. So we're encrypting letter by letter here. So you can think of the message space as being just all the letters. And the ciphertext space is also all the letters. And in the Caesar cipher, there's only one key, which is 3. So for a given key, which is 3, what you do is you just add the key mod 26, and that's the encryption function. And then to decrypt, you just subtract the key again. And you can, every time you set up so this is sort of a claim here. So I'm just claiming that this function, it really is the inverse of E. You should check that it actually is. So what if we compose the decryption and the encryption? It should cancel out, right? And it does, because the encryption is X plus K, the decryption takes K away, and so you get back to the original X. All right. So the Caesar cipher is the simplest possible cipher that might actually do something, and it's very insecure once you know how it works. Actually, once you know how it works, you can just undo it yourself. There's no secret that is shared by the sender and the receiver. In some ways, there is no key, because the key is always 3. So once you know how the system works, you can just decrypt anything you want. So that happens so commonly in cryptography that there's terminology for that. So when you just have some complicated system, and the security of the system depends on just nobody knowing this complicated encryption mechanism. That's called security through obscurity. And there have been a lot of, it's kind of amazing, you know, there's been a lot of ciphers in world history. Almost all of them have been broken. And anytime somebody has tried to use security through obscurity, that has led to disaster. So we don't do that anymore. In fact, this Russian guy who lived in the 19th century already knew that it was a bad idea. So we have, his name is Kirkhof. Claude Shannon was an American that was a World War II cryptographer. So they call this the Shannon-Kirkhof principle, which is one should assume that the enemy knows the system. Assume that the enemy knows everything but the key. Sorry, it's a typo. So there has to be some secret that's shared between the sender and the receiver, and then we're just going to assume that the eavesdropper knows everything except for that secret. And practice has shown that this is the best way to construct a cryptographic system, because cryptographic systems have to have users. So if you have 10,000 users, what are the chances that nobody is like a spy that's just going to reveal how the system works? Of course, somebody is going to, you know, accept a $10,000 bribe or something and leak it. So the security of the system has to depend on just a small secret that you actually have some hope of keeping secret, in which you can, you know, you refresh keys just like you change passwords from time to time. So it's a short secret, and you can refresh it, and that just works better. So now we're going to go on from the Caesar cipher to a more general substitution cipher. So instead of rotating forward by 3, you know, there's nothing special about 3. We can rotate forward by any amount that you want. So that's called the general shift cipher. So let's say that I gave you something encrypted with a general shift cipher, which I will, you know, before too long. Anybody think of like a strategy for breaking a shift cipher? People following along with the slides, don't scroll down. So if you and I are communicating, we share a secret, and the secret that we share is just some number between 0 and 25. I think the most obvious problem is that there's only 26 possibilities. So you can check that in like a nanosecond on a computer. One issue might be recognizing the plaintext when you see it. So cryptography actually uses probability theory quite a bit, because you would use probability theory, or the probability of the letter frequency distribution to recognize plaintext when you found it. Something like this, would you recognize that as being the plaintext? Probably not. But you would recognize like an ordinary English message. So written English has a certain statistical profile that's different from just numbers selected uniformly at random. So if the message had been compressed such that it sort of had no redundancy, and it just looked like a bunch of letters picked uniformly at random, that would strengthen the cipher and make it harder to recognize the decrypt automatically, or at all, possibly, when you found it through brute force. Also, we're going to introduce something here called a known plaintext attack. So if you intercept a message, like let's say that we see this go by on the wire, YVCCFDFD, then you might have some natural guess about what how the message begins. You know, like in when you're doing TCP packets, you know, often the first thing that's in a TCP packet is like some kind of header information or something like that. When it's an email, the initial word is probably hello or dear or something like that. So when you have some guess about what part of a message might be, that's called known plaintext. So let's just say that we guess correctly here that that this message begins hello. So that means that Y corresponds to H. So if Y corresponds to H, then you can immediately see Sorry, I just muted someone. You can just take the difference between y and h to figure out how far things were shifted. So 10 shifted forward by 17 is congruent to 1. So the guess that the first letter of the plaintext is h leads to the conclusion that the key must be 17. And then you can just try that, and then if you get a reasonable decrypt, then you crack the cipher. So this is KPA, known plaintext attack, and you have to remember that. So that's an important concept. All right. So now we're going to go through and for as long as we can, try to make these substitution ciphers more and more sophisticated, and then just keep breaking them. Because it's instructive to see what goes wrong. And even though there are no more substitution ciphers used in the world, substitution is still an important component of the strong ciphers that we do use. And so it's important to understand what the weaknesses are. So let's go on to the affine cipher. So this word affine is just a fancy, it's like a matrix operation followed by, it's a matrix multiplication followed by matrix addition is really what it is. So here we're not using big matrices. These are one by one matrices, you know, just numbers. So it's kind of a too much word for what's actually happening here. So the way this works is we're still going to be encrypting one letter at a time. Now the key is a pair of numbers, and the first number has to have a special property, which we'll talk about in a second. The second number can just be any number between 0 and 25. So to encrypt, you do a times x plus b mod 26. And then to decrypt, you invert that. So this shows you, if you're just doing algebra here, you know, how do you solve for y? Well, you move b over there, and then you have to multiply both sides by a inverse. So it's this a inverse thing that creates the requirement that a has to be a little bit special, because not every number modulo 26 can be canceled or divided out. It's just special numbers. So here this makes it a little bit more plain. So z sub 26 is the integers mod 26. So it's 0 to 25 is the simplest way to think of it. So b is just some number between 0 and 25. But a is in z26 star. So this is official notation. We're going to be using this all semester. So what does the star mean? It means that you only consider numbers that are relatively prime to 26. So that just means that the GCD is 1. So z26 star is all the numbers between 0 and 25, such that the GCD of the number in 26 is 1. That means they have no factors in common. And you can just quickly figure out what this is. This is called a Python list comprehension, and it's basically the same as this set builder notation. So we want a for a and z26 if the GCD of a and 26 is 1. So it turns out that that those numbers are 1, 3, 5, 7, 9, 11, 15, 17, 19, 21, 23, etc. So these are the ones that you can actually cancel out and invert. So let's go through here and do an example. So suppose we want to invert the affine cipher. So here's the initial equation. Then you start solving it, and you get y minus b. What you're trying to do here is isolate x. So now you want to multiply both sides by the inverse of a. You can't actually literally divide, because that might create a decimal number, but everything has to be a whole number. So it's not literal division. But we do want to kind of cancel it out. So let's look at a concrete example with these numbers. Let's say that x is 15, a is 9, and b is 2. So now that equation that we were looking at just becomes this expression. So we have y minus 2 is congruent to 9 times x mod 26. So now we want to cancel the 9. So it turns out you can cancel 9 by multiplying both sides of this equation by 3, because 3 times 9 is 27, but the remainder when you divide 27 by 26 is 1. So 3 times 9 is 1. So it's like dividing by 9 is multiplying by 3, modulo 26. So that lets you solve the rest of the equation here. So now you go on and you find that x is equal to 3 times y minus 2. And then if we plug in the numbers that we were using, we'll see that x is equal to 15. And x actually was equal to 15. So it all worked out. Yeah, so 3 is the inverse of 9 modulo 26. So in general, what it means to be an inverse for multiplication, the inverse of a modulo n is the number that we denote it here with a little -1. So that when you multiply those two numbers together, you just get 1 mod the modulus. And the reason we care about Z26 star is because it turns out a number has an inverse if and only if it's relatively prime to the modulus. And we could prove that, but we'll just go through and we'll check it with a little program here. So first of all, this is how you might find the inverse of 9 mod 26 using a little Python program. So you want all the b for b between 0 and 25 such that a times b is congruent to 1 mod 26. It turns out that there's just one number like that, which is 3. So we could do that for any number. So this function will find the inverse of a mod n in a very inefficient way, I should add. So what it will do is it'll just check all the possibilities and see if a times b is congruent to 1. And then it might be that it finds that there are no candidates, in which case it returns none, so that number doesn't have an inverse. And if a number is found, then this asserts that there's exactly one thing found. So either there's no inverse or there's precisely one inverse. So that's just a group. Yeah, sorry.
You kind of lost me. Can you please explain the code for the Python, where b for b in range of 26?
Yeah, so range 26, that's what we could also call this z mod 26. So this is just the numbers between 0 and 25 inclusive. And this condition here is that a times b mod n has to be equal to 1. So that's saying kind of the same thing as, so we want the product of the two numbers has to be congruent to 1 mod n. So that means if you take this product and you use mod n in code, so it's the same way in C and C++, if you do mod n, then that is, reduction mod n. So if b times a mod n is congruent to 1, then by this definition, you've found the inverse. And so a concrete example is 9 and 3. So 9 times 3 is 27, which is 1 mod 26. So this is a pair of inverses. And in general, a pair of inverses is just any two numbers, so that when you multiply them and reduce them mod n, you get 1. So given any a here, this checks all possibilities. So this is just an exhaustive check over the entire set Z26 to try to find another number so that when you multiply them together, you get 1.
Okay.
Okay. Thanks for asking, and please ask questions, because I just feel, like I'm talking to myself. If nobody is asking any questions, you're always welcome to stop me. Okay, so either there are no inverses or there's exactly one. That's just that's a group theoretic fact that will I guess we could prove it later. We could even prove it now, but I don't want to make things more complicated. And then you return the unique inverse if it exists. So we'll just go through every number between 0 and 26 and find its inverse. So the inverse of 0 is none. The inverse of 1 is itself. 1 times 1 is 1. 2 has no inverse. And if you look through this list, you'll see that the ones that are coming up none, even though I didn't put this into the program, the ones that are coming up none are exactly the numbers that have a factor in common with 26. So, so 2 has a factor of 2 in common with 26. 4 has a factor in common with 26. 6 has a factor in common with 26. And the ones for which the inverse actually exists, these are exactly the numbers that have no factors in common with 26. So those are exactly the numbers that have an inverse, and that's always true. So the numbers that have a multiplicative inverse mod n are exactly the numbers that have no factors in common with n. Even 0 arguably has a factor in common with 26, because 0 times 26 is 0. So you could say 26 divides 0. So I don't know. But people, if you write down the math, it is literally true that 0 and 26 share a factor of 26, even though that's silly because 0 just eats everything. Okay, and here, this is what the inverses are. So 7 and 15, maybe we can just check one of these. So 5 times 21, that's 105. No, right, it's 125, right? So let's insert another little cell here. 125 divided by 26, or sorry, mod 26 is, oh, that's not right. I must have calculated something wrong. But what is 5 times 21? Maybe I'm just too stupid to figure that out. Oh, 105. Yeah, sorry.
It's 105.
Yeah, it's 105. Oops. So then if you do 105 mod 26, then you get 1. So how many times does 26 actually go into 105? So this double division here is integer division. So so 26 goes into 105 4 times evenly with a remainder of 1. So 105 has a remainder of 1, so it's congruent to 1 mod 26. And so that is why 5 and 21 are a pair of inverses mod 26. And you could do that same thing for all of these, but the numbers get kind of big here. Also notice that if 3 is the inverse of 9, then 9 is the inverse of 3. So that it works the same way. They come in pairs. So 5 is the inverse of 21, and 21 is the inverse of 5. That's just because multiplication is commutative. You know, A times B is the same thing as B times A. So if A times B is 1, then B times A is also 1. So here's some notation. So in your homework, we use this notation. They also use it in the book. So you might see 1 over A mod n. So this is the inverse of A mod n. And they might also write it as a -1 for reciprocal here. But you don't literally take the reciprocal. So like the inverse of 3 was not 1/3, because 1/3 is 0.33. It doesn't make any sense. It's not even an integer. It's just a metaphor. So often in higher math, you use notation that is sort of a metaphor for what happened in the case that you're more familiar with. So this is sort of like reciprocation, but it's not literally reciprocation. It's just sort of works the same way in equations. You can use reciprocals to cancel things out in normal algebra, and you can use inverses to cancel things out when you're doing group theory, which is what this stuff is the beginning of. Okay. Okay. So we can look at the kind of permutation that the affine cipher creates, and so you can see that it's much more random looking than the shift cipher. So the shift cipher was kind of obvious. So it was just a circular rotation of these letters here, and they lined up with each other again. But now this actually looks kind of pseudo-random here. Like my eye doesn't see a pattern, even though there actually is we know that there is a simple pattern because this is an affine cipher. What we're doing here is we're using the affine cipher with A equals 3 and B equals 2. We're going through it and getting the number corresponding to the letter. Then you multiply by A plus B mod 26, and then you convert back to a new letter and then print them out. So that's where that correspondence is coming from. So this is an improvement from a cryptographic point of view. So this permutation of symbols is more random looking. And in cryptography, you have things that you can control with little parameters like A and B, but you want the result to look as random as possible to somebody who doesn't know what's going on. So this is better. I'm calling this a keyed permutation. So we might use that terminology again. So often in encrypting things is, if the message space is the same as the ciphertext space, which it is with what we're doing right now, because both messages and ciphertext characters are just they're just alphabetical characters, so they're the same set. So that's often true. Like if you encrypt 64 bits in a real modern cipher, what you get is a 64-bit ciphertext. So it's just like a permutation of 64-bit blocks of information. And then which permutation you actually use depends on which key you pick. So we'll call these things keyed permutations. So there's this huge space of permutations out there, and we'll be using a keyed subset of them, which is going to be huge if you have like 2 to the 128 keys, which you would with a 128-bit key. That's an enormous amount, but it's still much less than the number of ways to really permute all blocks of 64 bits of information. So what we're taking is sort of a tame subset of all permutations, and they look kind of like randomly selected permutations, but they're actually determined by the key information. Okay, so you can crack the Affine Cipher. Can anybody think of something that might go wrong with the Affine Cipher? It has one problem in common with just the shift cipher. So now, how many keys do you have? It's just you have 13 things in Z26 star, and you have 26 things in Z26. So there's 13 possibilities for A, and 26 possibilities for B, which is only 312 keys. So that's still something that your computer can check in a nanosecond. But you also still have what we call the known plaintext attack from before. So if you can guess, now you need to guess two things. So suppose that we have reason to believe that A corresponds to C and B corresponds to F. So then A is 0, C is 2, B is 1, and F is 5. So we can write down two equations that must be true. So it must be true that the encryption of A is C. So when you put in the numbers, that says, 0 is A. So 2 times capital letter A plus B is equal to capital C, which is 2. And you get another equation here from the correspondence of B and F, and that says that, B is 1. So we encrypt 1, and 5 comes out because 5 is F. So if our guess here about the plaintext is correct, then we get these two equations, and but this is two equations and two unknowns, and you can just immediately solve for A and B. This first equation tells you that B must be what?
Two.
Sorry, somebody was about to say it. What is B according to this first equation?
2.
Yeah, 2, right? B must be 2. And then once you know B is 2, then what does A have to be down here?
3.
Yeah, 3, because you take 2 away from both sides, and then 3 is equal to A times 1, so 3 is congruent to A. So from this known plaintext, you can immediately find the key. So A is 3 and B is 2. So this cipher is, we would say in fancy language that it's not KPA secure, because if you know some plaintext, if you actually know 2 letters, 2 corresponding letters, then you can crack the thing just by solving these equations. Okay. So now we're going to go up in difficulty again. So if a more random looking permutation was better, maybe a permutation that is literally random will be even better, which it is. So we're getting stronger and stronger ciphers here, even though they're still weak. Okay, so now let's just review what a permutation is from Math 204 or whatever. So you might think of a permutation as a rearrangement, which it is, but it's also a correspondence, which is just given by a function. So you might think of the same permutation as being a function. So a permutation is just a one-to-one function from a set to itself. you can always write it as a rearrangement, but what you're doing is you're just saying that, you know, A corresponds to D, et cetera. You're giving a 1-1 correspondence between the set and itself. So here, the same permutation is written sort of as a function, and this shows you where the characters go. All right. So here is a literal random permutation. So I use this library called NumPy, and then I seed the random number generator. And then we have to do some Python stuff, but this is the important thing. We're getting a random permutation. So basically this thing we call the scramble is a random permutation of the alphabet. And then we can look at their correspondence. So this permutation really is selected at random. But in cryptography, you always have to be careful. How random is this really? You guys know about the seed of cryptographic, the seed of random number generators? You know, the
They're all consistent.
Yeah, if I do this again, because I use the same seed, actually the same thing will come out, right? So you have to be careful, because maybe I'm doing this and I only use one of 3 possible seeds or something. Then all the enemy has to know is what the seed is, not what the permutation is. There's 26 factorial possible permutations. Nobody will ever guess our permutation, but they might guess our seed. And so little mistakes like that are behind like almost every kind of cryptographic disaster you see in the news. Somebody's supposed to pick a random number, but it turns out not really to be random, because there's actually like a small seed space or something like that. If you want to get true randomness from your computer, you can do that. Let me just do it here. So one way, you can open a terminal if you're using CoCalc, or you can just open a terminal if you're using Mac. You can do head. And so this will give me the top, I don't know, I'm going to get 16 bytes of randomness. And on Linux and probably on Mac too, you can think of it as like a hardware device. It's like the hardware random number generator. It gets it gets entropy, which you can just think of as randomness from all kinds of things that are happening in the real world, like the processor temperature and like packet delay and which keys the user is typing on the keyboard and how the mouse is moving. So it takes all these sources of randomness in the real world and produces random data. So you can't actually read those characters that came out, because they only a few characters actually print in ASCII. But we can put out that stuff in an output file and then look at it. So what I did is I redirected the output into an output file, and if I dump the output file to the screen, it still looks like gibberish, but I can use a hex editor like XXD to look at the output, and this will show me what the actual binary contents of the file are. So in hexadecimal, which we're going to be using a lot, so this is 16 bytes of real random data. So you can actually use it for cryptographic purposes. So that really is, the chances that we got this really is like some vanishingly small number, because it didn't depend on some small seed value. It's actual randomness that comes from just mechanical things in the real world. Another way to do the same thing is to use the OpenSSL random library. So if you get 16 bits of randomness. So you could do that to generate a cryptographic key, for example. So those are real random number generators. They're called TRNGs, true random number generators. And most random number generators are just PRNGs, pseudo-random number generators. And pseudo-random generators, you have to be careful with them, because you can think that something random is happening when it's really not. So we get this random permutation here. And we can encrypt something using this random permutation. So this is the plaintext, gets encrypted as this nonsense here. So this is an improvement from what we had before, because now the problem with all the ciphers that we've seen up until now is that the key space has been too small. Key space has been like 26 or 300 or something like that. But now the key space actually has a huge number of things in it. So you should have learned in 204 that the number of ways to permute n objects is n factorial. So 26 factorial is this number that I don't even know how to pronounce. It looks pretty big. You have to be a little bit careful, you know, like how big is it really for the purposes of cryptography? So you have this number. Is it a lot or a little? It turns out that this is a lot, even by cryptographic standards. So normally in cryptography, we measure security in bits. So if a system has n-bit security, it means that an attacker needs to try 2 to the n times before they're likely to crack the system by brute force. And just as a rule of thumb, 80 bits of security is what you need. You know, you might prefer 128 bits of security or even 256 bits of security, but at minimum you need 80. And so how many bits of security does the general substitution cipher have? So we need to solve this equation, 2 to the n equals 26 factorial. So you can do that just by taking log base 2 of both sides. And here's where I actually do it down here in the Python code. So you just do log of the big number, and then I put a 2 here because I want log base 2. And so the answer turns out to be 88. So this means 26 factorial is approximately 2 to the 88th power. It's actually 2 to the 88.38. So that means it's 88 bits of security, which is enough to have real cryptographic strength. So in this is our first example of a cipher where the weakness just doesn't come from the key space being too small. So it still has problems, but they're not as obvious. If you know a lot of plain text, then you can still do a known plain text attack. You know, like if you were able to see the encryption of the dictionary of just the alphabet, then you would know the correspondence between all the letters, and so that would destroy the cipher. So it still has some known plain text vulnerabilities. But even without that, there's another approach which is based on statistics.
Okay.
Yeah.
I have a question. Wouldn't all, I guess, wouldn't all cryptographic, I guess, wouldn't all encrypted data be vulnerable to plain text attacks, since
like all
once
encrypted
you know
data? Yeah, so how do you stop a known plain text attack from being an effective attack?
right.
Yeah. So we'll talk about that. It turns out that not only will the ciphers that we talk about be secure against known plain text attack, but the enemy can actually even choose the plain text, and still it doesn't matter. And one of the ways that happens is that real ciphers often have something called a nonce. Actually, since you like crypto, you might have heard of a nonce before. And a nonce is a number used once. And it doesn't have to be a secret, but it makes the ciphertext it affects the ciphertext. You mix it in to the encryption process, and it makes a different ciphertext come out every time, even if you're encrypting the same information over and over again. So the enemy can know the nonce, but not knowing the key, they don't know the effect of the nonce, and they just can't entangle things. I think it'll be the first serious cipher. I guess we'll look at serious ciphers next week, and I'll keep asking you about this. So keep your eye out and see if you see a way to do a known plaintext attack about any of the more advanced ciphers. Okay. All right. So it turns out that I don't know if we have time to get through this, but all substitution ciphers are insecure. And the reason is basically that they don't disguise the statistical nature of the plaintext. So if you look at like a long piece of English writing, the probability that a given character is A is the number of times A shows up in a book, let's say, divided by the length of the book. And then if A corresponds to F in the substitution cipher, even if it's using all the possible permutations as a possible key, then the probability of F in the ciphertext is still going to be equal to the probability of A in the plaintext. And it turns out that in English, the letter frequency doesn't depend on exactly which book or which paper you're talking about. Letter frequency turns out to be pretty much the same across all English writing, or English doesn't matter. It's also true of French, Russian, etc. So here's an example. I get a couple of books from Project Gutenberg, and then I read them in, and then convert them into all uppercase with no punctuation. And now let's plot the frequency. So in this first book, which is Shago, the Mighty Buffalo, these are literally the first books that showed up on Project Gutenberg. You can see that it occurs with frequency about I should multiply this by 100. So about 9% of the characters in the book are A. About almost 12% of the letters in the book are E. You can see that these numbers are pretty distinctive. Like and that's what's going to let us crack this when the time comes. Certain letters are very uncommon, like J and X and Z and Q. Those very rarely show up. So here's one book, Shago the Mighty Buffalo. Here's a completely different book written by a different author, probably in a different time period, in a different genre. But the distributions of the letters are almost exactly the same. And here, if you look at them next to each other, you can see that there's very little difference. So the frequency with which a letter occurs in English doesn't depend on which piece of English writing you're talking about. It's just a sort of a thumbprint property of the English language. Again, it would be true of German, French, Korean, etc. It doesn't matter. So you can use that to crack the cipher. Maybe since we're running out of time, we should just skip down here to the picture. So I encrypt one of these books, and then you can look at the letter frequency in the ciphertext. So in the ciphertext, F occurs about 12% of the time. So what letter do you think F corresponds to?
E.
E, right? And you can just read these things right off, like, so E is F because F is the most common ciphertext character, so it must correspond to the most common plaintext letter, et cetera, et cetera. So we're kind of out of time now. And I have to teach right after this. I can answer questions for just a little bit of time. Anybody have any questions?
So I have a question.
Yes, Justin.
Is it mandatory to get the textbook, or it's iffy?
You can get what I suggest you do is get the PDF. And yeah, I would definitely read along. Because I won't just be writing. I do have a lot of slides, but it's also good to read. It's good to read the textbook, especially when we get to some of the harder stuff, like the chapter on AES. You really need to carefully read that chapter. So I would get the textbook for sure. But you can just
you
can get the PDF.
And one more question. We have 3 websites for this one class. Which one's going to be mostly used for homework? Is it going to be web work?
For at least the next month, we're mostly going to be using web work until like, I don't know, maybe, I don't know if we'll ever, it depends on how much time I have to keep converting the book problems from book problems to web work problems. But we're going to spend most of the time doing homework on web work. And so right now, you already know enough to get started on your first homework if you want to. You have to crack these classical ciphers.
Are there due dates for those homeworks posted on this website?
Yeah, so if you go to, right when you log in, you'll see.
Okay, I see.
So chapter 1 is open, and it closes on
the 4th.
Yeah, the 4th, which is a week from tomorrow. I'm glad you.
Professor?
Yes.
I've been trying to log into WebWork, but it won't allow me to go. It gives me an authentication error.
Okay, just send me an email and we'll get it figured out. It might be that you might be in the habit of typing your CUNY login with some uppercase letters. So try it all lowercase. I think that's mostly the problem that people are having.
Okay.
Anybody?
Sorry, the chapter 2 homework on here, on WebWork, on your screen, it says due in 2 days. Is that correct?
Yeah, That's true. No, sorry, of course that's wrong. Thank you very much. So I'll change that. Just worry about the first homework.
All right.
Anything else? So, all right, I'm gonna stop sharing and stop recording. So I'll send everybody the